Hello, welcome in Science for Free channel, and this is Muhammad Alwi. Today we'll start the first episode in quantum mechanics, and in this episode we'll just introduce the basic idea and basic motives due to which quantum mechanics was emerged. Actually, the story almost began in 1900s when physics entered into a deep crisis of inability to explain some peculiar phenomena like photoelectric effect and compoton scattering, based mainly on classical physics. And by 1923, it was totally apparent that all these peculiar phenomena shared a common factor or common framework or common set of principles based on which we can effortlessly explain all these peculiar phenomena. The main concept of this new framework, which by the way was totally different from the framework of classical physics, the main concept in this new framework was the principle of wave-particle duality. The wave-particle duality in its simplest form states that for every particle there is a wave character, and also for every wave there is a corpuscular character. It's very important to mention that by wave character I mean frequency and wavelength. And by corpuscular or particle character, I mean energy and momentum of the particle. We have to discuss this very basic and very introductory concept to quantum mechanics by discussing how particles can have wavelengths and frequency. Also, how waves can have energy and momentum like particles. So let's get started with discussing it basically from two main aspects, which is the wave-particle duality of waves or light, and wave-particle duality of particles of or matter. Okay, so let's get started with discussing the wave-particle duality of light. I mean that how light can has some corpuscular characteristics, how light can has energy and momentum like particles. Okay, we have to consider a very important phenomena. Actually, there are two phenomena that were completely inexplicable based on the classical mechanics laws, but they are effortlessly explained based on the principle of wave-particle duality. These two phenomena are photoelectric effect and compoton scattering. Let's get started with the photoelectric effect. The photoelectric effect can be defined as the light-induced removal of electrons from physical systems they are bound to. Whatever these systems can be atoms, molecules, or even metal surfaces. Okay, the main point in this effect or photoelectric effect, the main point is inability of classical physics to explain a very, very important observation, I mean empirical observation, in which the photoelectric effect can occur only when the energy of the incident electromagnetic radiation is greater than or at least equal to a certain value. This threshold condition cannot be explained by classical physics. This is very simply because in classical physics, light or electromagnetic radiation is defined as synchronized oscillations of electric and magnetic fields. So whatever the value of the frequency of the incident electromagnetic radiation, it will produce a work on the electrons. So after a certain period of time, this work, when exceeds the work function or the minimum energy that is required for electron extraction, when exceeds the work function, electrons will be extracted or removed away from the metal surface. But there is no justification in classical physics to explain the threshold condition of the occurrence of photoelectric effect. I mean that there is no justification or explanation of why the incident electromagnetic radiation must be with a certain frequency or above in order for the electromagnetic radiation to cause photoelectric effect. Otherwise, photoelectric effect cannot occur. Quantum mechanics, on the other hand, considers light as a discrete packets of energy, not continuous electric and magnetic fields, but discrete packets of energy, which are photons. And when a photon is embedded on the metal surface, it can be absorbed by the electrons or passed away. And when the photon is absorbed by the electron, and the energy of the incident photon, this energy packet, is greater than or at least equal to the work function of this metal, so it will be absorbed and causing the electrons to be released away or removed or extracted from the metal surface, and hence the photoelectric effect can occur. Otherwise, the photoelectric effect cannot be occurred. If the absorbed photon has much greater energy than the work function of the metal from which electrons are emerged, then some of this energy photon can be absorbed and used for releasing the electron, and the remaining will be used by the electron as a kinetic energy, half mv squared, as we know. So we can formulate the very, very basic concept of quantum mechanics in a very simple relationship, which is the energy of the incident photon, which is the Planck constant times the frequency of the electromagnetic radiation, equals the work function of the metal plus the kinetic energy of the released electron. And this is called the Einstein's photoelectric equation. And by the way, it's noteworthy that the work function is stable for every metal, as we mentioned. So there is a direct proportionality. It's very, very clear that there is direct proportionality between the photon energy and the kinetic energy of the released electrons. So we can confirm or even disprove the Einstein photoelectric equation just by measuring the kinetic energy of the released electrons versus different energies of the incident photons. And if we find the kinetic energy of the released electrons dependent linearly on the energy of the incident photons, then the Einstein's photoelectric equation can be proved. And by the way, this is a direct confirmation that the light is not a continuous electromagnetic radiation, but it's like a discrete quanta, discrete, not continuous, discrete quanta of energy packet. It has somehow a character of the particle. It's a discrete, not a continuous. It's discrete like particles. Each particle has a discrete energy based on its mass. And also, if we confirm this equation, I mean the Einstein's photoelectric equation, we can confirm that waves, or in more precisely, photons are discrete quanta of energy, like particles are discrete masses also, or discrete energies. Okay, in the next video we will consider the experimental setup that was used experimentally to confirm the Einstein's photoelectric equation, and how to use it to confirm the wave-particle duality of light. Thank you very much for watching, and see you later.